It's incredibly easy to take a map for granted. You look at it, you see where you're going, and that's usually that. But what you're actually looking at is a total marvel of mathematical engineering. Let's dive right into this explainer and uncover the hidden engine that actually makes geography and cartography work in the real world. We usually just assume a map is this handy little illustration, right? Just a visual to get from point A to point B. But talk to a professional cartographer or a field engineer and they'll tell you something completely different. To them, it is a rigorous calculation of compression that literally dictates the absolute limits of reality. It's what we call the silent engine of geography. And that engine is map scale. Think of it as the mathematical bridge between the Earth's massive, irregular surface and the manageable representations we use as professionals. Scale isn't just some cute little label tucked away in the corner of a page. It is a high-stakes engineering constraint. I mean, every single unit of ink on that map absolutely must correspond to a verified physical reality. If you ignore that ratio, the integrity of your entire spatial dataset is completely compromised.
To really master this math today, we're going to cover the mathematical bridge, the languages of scale, the large-scale paradox, the cartographer's constant, the squaring effect risk, and finally, operational precision.
Let's start with Section 1, the mathematical bridge, and how we have to treat mapping as a strict engineering constraint.
When you get right down to it, the strategic utility of any map relies on 5 absolutely critical functions. We use scale for distance acquisition, so figuring out precise ground distances. We use it for area estimation to calculate total surface areas for things like massive infrastructure projects. It gives us reduction quantification, so we know exactly how much the real world was squished down. It allows for spatial relationship analysis, basically seeing how different locations interact with each other. And finally, operational planning, because again, every drop of ink has to correspond to physical reality so that life-critical operations don't fail out in the field.
Moving right along to Section 2, the languages of scale, and why choosing the right one dictates your map's resilience.
Now, cartographers basically rely on 3 primary systems, or languages really, to express how the map relates to the ground. We have the text-based statement scale, the visual linear bar scale, and the numeric representative fraction, or RF. And here's the kicker. Which one you choose fundamentally determines how resilient your map actually is when it's put to the test.
Let's break these down. The statement scale, something like 1 centimeter represents 1 kilometer, is super accessible. But professionals call this the fragile text. Why? Well, think about zooming in on a digital map. The text on the screen stays exactly the same, but the actual map size changes, which makes the statement instantly false. That brings us to the linear bar scale. This is your mandatory zoom-proof hero. Because it's drawn directly onto the map itself, it shrinks and grows in perfect proportion to the data. Then we have the representative fraction. This is our mathematical diplomat. It's a unitless ratio, like 1 to 50,000, which is fantastic because it works in literally any country. But, it does require a bit of mental gymnastics to actually use while you're out there in the elements.
Okay, let's look at Section 3, the large-scale paradox, or why small is actually big. So our brains naturally want to think that a large-scale map covers a large area, right? It makes sense. But in cartography, it's actually the exact opposite. A large-scale map covers a really small, localized area, but with intense, high-intensity precision. For example, at a scale of 1 to 10,000, you can see crystal-clear building footprints. On the flip side, a small-scale map covers vast, huge regions, like an entire country mapped at 1 to 1 million. On that map, those exact same buildings just become microscopic, invisible little points.
It seems super weird until you just look at the math. The paradox is totally resolved by fractions. 1 over 10,000 is simply a much larger mathematical number than 1 over 1 million. It's like pizza, right? One slice out of a 10,000 slice pizza is way bigger than one tiny slice from a million slice pizza. Once you wrap your head around that logic, you will literally never miscommunicate your spatial data requirements again.
Next up is Section 4, the cartographer's constant. This is all about bridging the gap.
I need you to burn this number into your brain, 100,000. For metric users, this is the cartographer's constant. You get it by simply multiplying the 100 centimeters found in a single meter by the 1,000 meters found in a single kilometer. It is literally the absolute cornerstone for bridging the gap between map centimeters and ground kilometers, and doing it with true engineering-grade precision.
So, what this constant actually gives us is this fantastic, rapid, mental shortcut. You just move the decimal 5 places, and you can instantly convert your units. Move it 5 places to the left, boom, Centimeters turn into kilometers. Move it 5 places to the right, and your kilometers jump right back to centimeters. It's such a simple trick, but it absolutely ensures your units are standardized before you try to tackle any complex math.
Okay, so how do we use this trick to find our universal representative fraction? You just follow a really strict 3-step logic flow. First, you standardize your units. Use that 100,000 rule we just talked about to convert ground kilometers into centimeters. Second, you establish your raw ratio by writing the map distance and the ground distance side by side. Third, simplify it. Just divide both sides by the map distance. Following this exact logic flow takes any localized measurement and transforms it perfectly into that universal mathematical diplomat, the RF.
Now, how do we actually put that RF to work? Let's say you need to figure out exactly how long to draw a road on your map. It's easy. You simply take the actual ground truth distance and divide it by the scale factor, which is just the denominator of the RF you just calculated. That one formula turns real-world logistics straight into precise ink on a page.
All right, moving to Section 5, the squaring effect risk. This is the incredibly dangerous trap of area calculation.
This is a really crucial point. You can never, ever apply a linear scale directly to a 2D surface area. Because area is two-dimensional, it expands exponentially compared to linear distance. So to calculate area properly, you absolutely must use the area scale formula, which means squaring the scale factor. So check this out. If your map has a linear scale of 1 to 50,000, your area scale is definitely not 1 to 50,000. It is actually 1 to 2.5 billion. Crazy, right?
Just look at the gravity of this warning. If you forget to square that scale factor, your logistics, your fuel, your time estimates, they won't just be a little bit off. They will completely and utterly collapse your entire operation. You could literally end up ordering enough concrete to pave a single small driveway when you actually needed enough to pave an entire city block.
Which brings us to our final section, Section 6, Operational Precision, and how we go about mitigating catastrophic failure.
To avoid those massive failures, cartographers rely on some mandatory operational protocols. First up, standardize your units early. This completely prevents compounding errors down the line. Second, deploy precision instruments. On a 1 to 1 million map, an error as tiny as a 1 millimeter slip of your ruler instantly multiplies into a life-critical 1 kilometer wide error out in the field. Third, obey the rounding rule. Never ever round your numbers during intermediate steps, because that tiny little decimal error gets multiplied by a massive scale factor. And finally, the verification protocol. Always cross-check the visual bar scale against the written statement scale, because if they don't match, it means your map was resized without authorization, and that written text is now mathematically false.
When you really think about it, scale truly is the silent engine of geography. It's this invisible mathematical force that transforms the immense, wild complexity of our planet into absolute operational precision. So, the next time you consult a map, I really want you to try and look past the symbols and the labels and ask yourself, how is the cartographer's invisible math secretly shaping your reality right now? Thanks for hanging out and exploring this with me today, and I really hope this explainer completely changes the way you look at the world.